Hello, year 13s. Welcome back. Hope you had some rest over the half-term break. We are moving on to the last part of waves, which is stationary waves. Okay. So in the beginning, we are going to see what are the basic properties of stationary waves. How is it different from the normal waves we have studied so far? So the waves that we have studied so far, the transverse and longitudinal waves, they are progressive waves. Okay, they transfer energy. That is why we call them progressive wave. They transfer energy in the direction they are moving. So stationary waves are different. We'll see how they are different. So for stationary waves, we actually need two waves. Okay, it's not a single wave. We need two waves. So we need two progressive waves. They are of the same frequency and ideally the same amplitude. That would give you the best results. They are traveling in opposite directions and they superpose with each other. For example, I have a wave like this that is traveling towards the right, and I have a wave like this that is traveling. They don't look the same at all, do they? Let me see if my rubber will work. Yeah, it does. Okay, so I have another wave like this. Now it looks somewhat the same. So keep in mind they should be ideally looking exactly the same. Okay, so I have two waves like this. They're traveling in opposite directions. They should be having the same frequency and ideally the same amplitude. When they mix with each other or when they superpose with each other, what happens is we get a pattern like this. Okay, we get a pattern like this. So what happens is at some places where they are not in phase or at places where they are in anti-phase, when those two waves are mixing, they will cancel each other, and these are those regions where they are cancelling each other and they result in no displacement at all. Those regions are called the nodes. Okay. So a node is a region where the displacement is zero. The amplitudes of the waves that are mixing will cancel each other at those places. Why do they cancel each other? Because they are in anti-phase. Then places where they are in phase, the amplitudes add up and you get the maximum amplitude. And those regions are called antinodes. So antinodes are regions of maximum amplitude and nodes are regions of minimum or zero amplitude. What happens at the antinodes? The waves are in phase and the amplitudes add up and we get the maximum amplitude. Since we said they will be the same amplitude, basically what we get in at those antinodes will be double the amplitude. Okay, does that make sense? So a stationary wave is formed when two progressive waves of the same frequency and same amplitude traveling in opposite directions. So don't forget that. Traveling in opposite direction superpose with each other. And when they are superposing like that, in some areas, if you talk in terms of interference, in some areas constructive interference and in some areas destructive interference are taking place. So here, just because it is just two waves, we don't generally use that term. So in some places where they are in antiphase, the amplitudes cancel each other and you end up getting nodes. And amplitude cancel each other means their displacement is zero. And since they don't have any amplitude, actually in those areas, the intensity is also zero. And places where the waves are in phase, the amplitude adds up to give you an antinode. And since the amplitude is maximum, our intensity will also be maximum. And the distance between two nodes or two antinodes is always lambda over 2. So if I call these as A, B, C, D, E, F, say G. So we can see that B, D, and F are antinodes. So the distance between B and D, as well as the distance between D and F, is going to be lambda over 2. Then A, C, E, and G. This is supposed to be G. So AC is equal to CE is equal to EG. All these are equal to lambda over 2. The distance between any two consecutive nodes or two consecutive antinodes is lambda over 2. Now, why do we call them stationary? Why don't we call them progressive anymore? The answer is there now. Since the waves are traveling in opposite directions, there is no net transfer of energy. And that is why we call them a stationary wave. Then, if you consider two nodes, okay? If you consider any two nodes, I'm going to just clear some space for me here. So if you consider any two nodes or any two antinodes, it doesn't matter which one it is. If you consider any two nodes or any two antinodes, the particles inside them will always be in phase. For example, I'm considering A and C. Any particle at any point between A and C I consider, they are going to be in phase. Between two nodes, all particles are in phase. And between on both sides of two nodes, for example, say I'm considering this 2 points and say 2 points here. Those 2 points, do I need to go for 2 points? Let me just, I deleted the, say this is the line, this was a thing here. Say if I have 1 point here and then I have 1 point here. Those 2 points will be in anti-phase. So between two nodes or between two antinodes, the points will always be, sorry, what did I say? I think I have confused you. Between two nodes, always the points will be in phase. On either side of two nodes, on either side of a node, which is say this point and this point, they will be in antiphase. Okay, so these are the main properties of a stationary wave. Now, a very common exam question is for a couple of marks, what are the similarities and differences between stationary and progressive waves? Okay, so I have put that as a table here. It's the same thing from your textbook. Progressive waves, the energy are transferred in the direction of the wave. Here there is no net transfer of energy. In the case of progressive wave, a progressive wave is a wave that we draw like this. In that case, where what we call as a wavelength, this distance is a wavelength. If you're talking about this point, then this point and this point, this distance is a wavelength. So wavelength is the distance between two adjacent points oscillating in phase. But in the case of stationary waves, what did we say? Between two nodes, if you have two nodes or two antinodes, the distance between two nodes or two antinodes is lambda over 2, right? So what is wavelength? Wavelength is, you take 2 to the other side, it becomes twice, isn't it? Wavelength is double the distance between two adjacent nodes or antinodes. Then in the case of a progressive wave, as you are going from one end of the wave to the other, the phase keeps changing. But in the case of a stationary wave, we said just in the previous slide, we said between two nodes, all the points will be in phase. I have written nodes here. It should be nodes. So all the parts of the wave between two nodes is in phase, and on opposite sides of the nodes, it is in anti-phase. Then we just talk about one amplitude in the case of progressive waves. We just say the amplitude of the wave is this. But in the case of stationary waves, we specify a maximum and a minimum amplitude. At the antinodes, they have maximum amplitude, and at the nodes, they have minimum amplitude. Now, one of the most important application of these stationary waves are in these stringed instruments. Okay, so they produce musical notes from the stationary waves formed on their instruments. So now if say we have a string, okay, if it is fixed between 2 points, for example, I have a nail here, I have a string tied to that nail, and then it goes over a pulley and I have a weight here. Okay, so now this acts as a fixed end and this acts as another fixed end for that string. So if a string is stretched like this between two fixed ends, say A and B, and then say you are plucking the string at one end, what will happen? A progressive wave will travel through the string, hit the fixed end on this side and come back. So now what we basically have is we have two progressive waves traveling in opposite directions. So they will superpose and they will form a stationary wave. Now, the most simple form that you can get is the fundamental mode of vibration. It is a minimum frequency. For that, basically, we will have a single pattern like this. Okay, just two nodes and one antinode. So one thing you need to keep in mind is if you have a fixed end, at the fixed end, you always get a node. Okay, then the most simple pattern that we can form with two ends fixed are two nodes at each end. So this pattern that you see, which goes basically like this is the fundamental mode of vibration, and the frequency corresponding to that is called the fundamental frequency. It is a minimum frequency of a stationary wave. It depends on three things: the minimum frequency, it depends on the string's mass, it depends on the string's tension, and it depends on the string's length. Okay. Now, what we are going to see next is we are going to see, other than this fundamental mode, what are the other frequencies that is available. Now, in such a case, what can we do? We can find out the wavelength, and from the wavelength, we can find out the frequencies or the speed, whatever they are asking you in the question. Okay, so the lowest frequency is called the fundamental frequency, and the higher frequencies are called the harmonics. Now we are going to see how do the other harmonics look like with respect to the fundamental frequency. Okay, so finally let's see how the harmonics are related to the wavelength. So the first harmonic is where? First harmonic is our fundamental frequency. Yeah? So if you have two fixed points, fundamental frequency is always at the fixed points you will have node. You can't make it simpler than this, isn't it? The most simple pattern is where between the two nodes, you have nodes at the two ends, and then you have an antinode in between. So say the length of the string we used is L. Okay. We also know that from this end to this end, say from A to B, it is two nodes, so it is lambda over 2. The distance between two nodes is always lambda over 2. We also know that the distance between the two nodes in this case is equal to L. So lambda over 2 is equal to L, or lambda is equal to 2L. Okay, so that is what happens in the case of the first harmonic or the fundamental frequency. So let's say that the fundamental frequency is F0. Okay, so that is our fundamental frequency. Now, thinking about the second harmonic, what is the next simple pattern we can get? Again, at the two ends, we need to have nodes itself. So it can be, this is the most simple pattern we can get, isn't it? So we had 2 nodes. Now we have 3 nodes. A, B, C. From A to C, we are using the same length of the wire. So we haven't changed the length of the string. So from A to B, it will be a lambda over 2. From B to C, it will be a lambda over 2. So the total length in terms of lambda over 2 is lambda over 2 plus lambda over 2. And that is equal to our length. Okay. So lambda is equal to the length. So this one, which is the second harmonic. So this is the second harmonic. In the second harmonic, the wavelength of the wave is the same as the length of the string. In the first harmonic, the wavelength is double the length of the string. And what will happen to the frequency is, if this is whatever you call this frequency, the fundamental frequency is F0. If we call this F2 because this is a second harmonic, we can say F2 will be equal to 2 times F0. Okay, 2 times. Then, if we think about the third pattern, how many nodes should be there? We started with 1, we became 3. Now we should be going to 4. So we can go like this. Okay, 1 node, second node, third node, fourth node. So this is a lambda over 2. This is another lambda over 2. This is the third lambda over 2. So lambda over 2 plus lambda over 2 plus lambda over 2 is equal to the length L. Because each case we are using the same length of the wire. We are just changing the frequency at which the wire is going to oscillate. So 3 lambda over 2 is equal to L, or L is equal to 2 over 3. Or lambda is equal to 2 over 3 L. Okay. So that is how what the wavelength is in the case of third harmonic. So in the terms of frequency, the third harmonic frequency will be 3 times the fundamental frequency. The second harmonic was 2 times the fundamental frequency. Third harmonic will be 3 times the fundamental frequency, and it goes like that. Let's do 2 more so that it becomes clear to you. So if you think about the previous slide, what did we have there? If you think the first harmonic, we had 2 nodes there, isn't it? 2 nodes at the fixed ends. The second harmonic, we had 3 nodes. 2 nodes at the fixed ends and 1 node in between. Then we did the third harmonic, which had 4 nodes. So first harmonic has 2, second harmonic had 3 nodes, third harmonics had 4. So how many nodes will the fourth one have? It will have 5 nodes. And the fifth one will have 6 nodes. Okay, so let's look at the fourth one first. So we need to have 5 nodes there. So 1, 2, 1, 2, 3. I think we need to stop there. Okay, I might end up losing all of them. So if I draw it like this, 1, 2, 3, 4, 1, 2, 3. Now I have 1, 2, 3, 4, fourth harmonic. So I need to have 1 more, 5. Okay, so this is a lambda over 2. This is a lambda over 2. This is a lambda over 2. And this is a lambda over 2. So totally, how many lambda over 2 I have? 4 lambda over 2 is equal to L. Or lambda is equal to L over 2. Then how did we say the frequencies are? If the first frequency was F0, the second harmonic was 2F0, the third harmonic was 3F0, So this will be 4F0. Okay, and let's see one more, the fifth one. 5 means we should have 6 nodes for the fifth harmonic. So 1, 2, 3, 4, 5, and 6, isn't it? First node, second node, third, fourth, fifth, and sixth. So we have a lambda over 2, we have a lambda over 2, a lambda over 2, a lambda over 2, a lambda over 2. Where is all these lambda over 2 coming from? Because all these are the nodes. Then distance between two nodes are lambda over 2 always. So we have 5 lambda over 2. And again, the length is the same for the string. So finally, we have lambda as 2L over 5. And the frequency will be 5F0. Now, what type of questions will you get? For example, they will tell you that this whole length is 30 centimeter. In that case, find the wavelength. So that means 5 lambda over 2 is equal to 30 centimeter. You can find lambda from that. Then they might give you the frequency already and they will ask you to find the speed. Speed is equal to frequency times wavelength. I would not use like C here just means speed. So don't confuse C with the speed of light. I would say V equals F times lambda. Okay. So these are the stationary waves on the string, the fundamental and the higher harmonics and all those things. We have one more that is left, which is what if both the ends are not closed, or both the ends we don't have nodes. That we will see next lesson. So go through this and then try answering the questions that I have mentioned, and we will see the next lesson and get it cleared. Okay then, bye-bye.